Thank you so much, Suzanne, for sharing these beautiful insights with us today. And now we're thrilled to have Andrea Ghez with us today in a fireside chat in which we will discuss her work, for which she, as you probably know, received the Nobel Prize in Physics at the end of this last year. Andrea earned her bachelor's from MIT in 1987 and her PhD from Caltech in 92. Since 94, Andrea has been at UCLA. She's now Professor of Physics and Astronomy and the Lauren B. Lightman and Arthur E. Levine Chair in Astrophysics at UCLA. She's joined today by many of her students from UCLA as well, so welcome all of you. Andrea is one of the world's leading experts in observational astrophysics and heads UCLA's Galactic Center Group, one of the premier groups in the world. She's also very committed to the communication of science to the general public and inspiring young girls into science. Her work can be found in many public outlets as well, including TED, Nova's Monster of the Milky Way, Discoveries, Swallowed by a Black Hole, which sounds really scary, TED, and the Griffith Observatory. Andrea, thank you so much for being here with us today in this little fireside chat with me to celebrate women in data science on International Women's Day. And I very much appreciate you taking your Sunday afternoon to be here with us. Now, my newspaper said this week, and I'm going to hold this up, and maybe you can see it. Space is the place, it says. So here in Bend, Oregon, where I am right now, they know this. Now you're very far into space in your research and you study the galactic center of our Milky Way galaxy. That's pretty far away. I think it's around 25,000 light years or so. Quite the journey. And your work is about studying black holes. You discovered, for example, that at its center, the Milky Way has a supermassive black hole. So my first question to you really is, what were the breakthroughs that allowed you and your team to find that out?
Well, thank you for having me here. It's just a delight to be able to chat with you. For me, it's this afternoon. Well, it's key. A lot of things were key in enabling the work at this moment. And I think the most important piece was the technology. So one of the key ways in which we do the work is we first need to discover stars at the center of the galaxy, and then we watch how they move under the gravitational influence of whatever's in the middle. So you need to be able to see stars that are as close to the heart of the galaxy as possible. So one of the fundamental challenge to this work has been the distorting effects of the Earth's atmosphere. So in spite of the fact that we have very large telescopes on the ground, which in principle allow you to see very fine detail, the atmosphere blurs our images of astronomical sources. So being able to implement methods and technology that overcome the distorting effects of the Earth's atmosphere is really the key to this work. And we've been really fortunate in the sense that over the last 20 years or 25 years, there's been tremendous progress in the way these technologies and methodologies work. So the work has just gotten richer and richer with time.
Yeah, so I was reading a little bit about this. I know very little about black holes. My son knows a lot more than I do. But they're very mysterious things. And I wonder how you started really getting interested in this. What made you study this particular aspect of space?
Well, as we were just hearing, telling our stories is such an important part of what we do. But of course, hindsight's always 20/20 in terms of how did we get to where we are today. So the narrative that I can tell is I got interested in space by the early moon landings. I was 4 years old, and that certainly opened up the concept and excitement of space to me. I think for me, understanding the scale of space, both in space and in time, really captured my imagination. And I really got interested in questions associated with the boundaries of things. What is the beginning and the end of time? What is and where do space and time mix? Which is really what makes black holes so intriguing to physicists. Is that these are objects where the pull of gravity is so intense that nothing can escape them, not even light. But what that also means is that it's a region of the universe in which space and time are becoming coupled or enmeshed with one another. So that, I think, is what got me interested in these things. I actually went to college wanting to be a math major, and because I think so many of these concepts are really best studied through math. And yet, by the time I was in college, I really understood that it was the physics approach that really appealed to me. But ultimately, I think it's the combination of the physics as well as just the interest in puzzles. I view so much of research as just giant puzzle solving. So I'm really interested in developments of methodology, the tools in which we use to make these discoveries possible. And I guess, apropos of the topic of this conference, increasingly, the connection to data science is becoming more and more important to the work. The work has been going on for the last 25 years. So we have this data set that you have to keep together, which has its own interesting data issues associated with being able to access, being able to understand the provenance of data sets, and using more and more sophisticated techniques that allow you to really maximize your understanding of what the data sets hold and your ability to understand and model correctly all the various correlations that run throughout our data set. So I'd say we're still quite naive in many of our approaches, and really could stand to learn a lot from this community.
Yeah, I was going to go to that question for sure. I mean, studying this, you do this through the telescope data, of course, and the volume of data that you will have studied to make your discoveries must be ginormous. And so I was going to ask you about this to give the audience a sense of the role that data plays, how big the data stream is that you're looking at, and what sort of tools you and your team and others needed to develop to actually analyze the data and maybe even store and see it and mine it.
Yes. So the techniques have evolved. So what we need has also evolved. In the early years, we used a technique called speckle imaging, where you take very short exposures, images that allow you to disentangle what the atmosphere is doing from what the true object is above the atmosphere. So I often joke that our job is to take the twinkle out of stars, because it's actually the atmosphere that makes stars twinkle. And in that sense, there's a lot of so it's basically a set of images. So we take thousands and thousands of images every night in the first decade, and it was then a question of deconvolution techniques. So it's a lot of coding and a lot of just figuring out the best way to unpack what the atmosphere is doing versus what the physics is doing. I think I suspect that the volume of data that we have, it was small compared to what many people in this field think about. So we today, after 25 years, we have on order of tens of terabytes of data. So while I think our challenges could benefit from data science, I realize that this, compared to a lot of data sets, is rather isn't very large.
Oh, I've worked on many data sets that are a lot smaller than this. I think data science, covers the spectrum from what we call working with small data to working with big data. But this is reasonable. You have a right to be part of this data science community, the big data community, with your volume. But you've been using the Keck telescopes, right, in Hawaii for this work. And I've been reading and hearing about this extra large telescope that they're hoping to build next the 30-meter telescope. What do you think a bigger telescope like that may give us for insights in the galaxy that we don't have right now? What are you hoping
Oh, so
that sort
much.
of technology works? Yeah.
Yeah, tremendous amount actually. So, large telescopes are beneficial for astronomical science for two reasons. One is that you can see things that are much fainter as your telescope diameter, which is the primary mirror, gets larger and larger. But you can also see finer detail, which is the aspect of big telescopes that I care about. So, the resolution, your ability to see fine detail, or you could say the angular resolution, goes as your observing wavelength divided by the diameter of your telescope. So the bigger your telescope, the more fine detail that you can see. The analogy I like to make is if you think about the technique of pointillism, where you paint by with dots, this is equivalent to getting closer and closer to the painting. So the larger your telescope is, the finer the detail that you can see. And in the kind of work that we're doing, the increase or the improvement goes as the diameter to the fourth power. So the fact that you might say it's only 3 times larger compared to Keck, this 30-meter telescope, but the improvement is really more like a factor of 80 because of that d to the fourth effect. Scientifically, what this buys you is so much. You can get a lot closer, and you can see many more stars. Today, we really only see the tip of the iceberg. The brightest stars are the not as closely packed. So as you try to see fainter and fainter things, you become what's called confusion limited because your stars just blur into one another. So today we really only see the brightest stars at the center of the galaxy, and they don't conform to what we expect to find around a supermassive black hole. In fact, almost every prediction for what you should see near a supermassive black hole has been inconsistent with the observations, which I like to joke. It's like job security. There's tremendous more to learn. But this 30-meter telescope will allow you to see the fainter things. The other analogy you could make in terms of understanding what's going on is that by only looking at the brightest stars, which is all we can see today, it would be like trying to understand the economy by only watching or seeing the largest financial transactions and not seeing the much more prevalent but smaller transactions. So the 30-meter telescope will allow us to see a typical star, a star the mass of our sun, at the center of the galaxy, and will hopefully elucidate a lot of our theories about how central supermassive black holes should interact with their host galaxies.
So you're a little bit nervous about this. You have all these beautiful theories that you've developed, and now you're going to learn a little bit more about how how valid they really are.
Oh gosh, it's so interesting in terms of how we as scientists approach um, uh, our fields and what and in terms of like what our response is. I have to say I find it most exciting when things don't work, in the sense that it's when there's much more to be learned. It's when the potential for discovery is high. When things conform to the way you expected, you're not learning a tremendous amount. You're confirming what was previously thought. But when things don't work, you have to think very carefully because, of course, things cannot work because you simply aren't analyzing your data correctly. And in our case, where so much of our work is built upon putting 25 years of data together, there are a lot of ways to go wrong because you can get the accumulation of small errors, or you can not understand the statistical properties of how you bring these various lines of data together. But I find it tremendously exciting when things don't work, or when your technology opens you up to exploring these new domains.
What has been the biggest surprise for you in these last 25 years? You know, things you thought you knew how they would work, and then you realized after doing the analysis that you were wrong and you had to adjust your thinking.
Oh gosh, there's been so many of them actually. Um, uh, I think one of my favorites was when we discovered young stars in the vicinity of the black hole. And the reason this was interesting or intriguing is that the anticipation is that in the vicinity of a supermassive black hole is that there should be no young stars. A supermassive black hole should suppress the ability to form stars. In fact, it makes an environment that's inhospitable to star formation. To get stars to form, you need gravity to overcome to be the dominant force in a cloud, so the cloud can collapse to be a star. But these clouds are really low density to begin with. They're very delicate in a sense. And when you put these delicate clouds near a supermassive black holes have what's known as tidal forces. Tidal forces is what creates the waves that the surfers care about so much. And I'm in LA, a lot of people surf. But those tides, when they're more extreme, will tear things apart. It's a process that in astrophysics is called spaghettification, so the elongation of objects, and that's the exact opposite of what you need to get stars to form. So the prediction is no young stars, and yet what we see is that the dominant kind of stars that we see are really young stars. And in our field, a young star is just a few million years old. To anthropomorphize stars, that would be like the human gestation period. So these are very, very young stars. So I like to call this problem the paradox of youth. How do you get star formation happening in this inhospitable environment? Everything about this environment is extreme, actually. You can think of the center of the galaxy like a crowded, exciting urban downtown area, like a metropolis. And where the sun is like the suburbs. We live in sort of the calm, low density, nothing too exciting happens. So it is really interesting to think about how this process that's so important to our understanding of galaxies and the universe happens under much more extreme environment. And in fact, the early universe is thought to be much more extreme. So you can actually, one of the ways that this becomes an interesting problem from another perspective is that the early universe should be much more extreme. So often people think about the center of the galaxy as a proxy for understanding what might be happening in the early universe. So we're intrigued by the problem. And it's been fun to dissect or to try to figure out, like, how do you get clues? And that original problem of the existence of young stars emerged in the early 2000s. And as our project continued forward, first you get orbits of stars really close to the black hole, which is what told us about the existence of a supermassive black hole. But over time, you can see orbits of stars that are further out. The orbital period increases as you get further away. And one of the beautiful things that emerged is that the young stars at one radius, at a certain distance from the black hole, start to line up. So rather than being random, start to fall in a common plane. And that's been an important clue for us in terms of how these stars might form. And this is maybe another arena in which there's interesting connections with data science, because you have partial information for a large number of stars. So how do you understand the population statistics or behavior of these stars? And one of the things that emerged from that analysis is that these young stars seem to form in a disk. So it looks actually quite similar to a scaled up solar system, which has been fun to make that connection with yet another field.
Yeah, I was thinking about this as you were talking earlier, when you drew this analogy with the financial markets. It seems that a lot of the work you do is uncertainty quantification, which of course is a very well known theme in other areas as well. So this cross fertilization of fields, maybe through the field of data science, is very interesting to think about. Let me take you to the future a little bit. I mean, you talked about
actually, Margot, before we go on, maybe we can actually build on that. Because we've had two really interesting collaborations that I would never have anticipated. And one is with a professor, Francis Longstaff, in the business school. Because of course, in finance, they care about the characterization of the market, which is variable. So one of the things that we look at is the the variations of the properties of the black hole itself. It's not actually itself, it's the accretion process. And it's very variable. And you want to know whether or not the black hole is reacting to anything around it. But since it's already variable, how do you know if something's changing? Of course, economists care about this a lot. You want to know if there's a new market state that's emerging. So we were able to use or to collaborate with him on these with these techniques that are used to characterize multiple states. And one of the key things was how do we describe our data and the uncertainty in our data. The other collaboration that's been a lot of fun has been with actually Chris Borgman, who's in information science, and we've collaborated with her on understanding almost the complexity of our data sets. So what are the problems that we're facing? And it's been so helpful to work with somebody in this field to help us articulate or find the vocabulary to describe some of the challenges that we face 25 years into this project.
Yeah, I can see those collaborations. I was thinking myself about maybe collaborating with people in say subsurface modeling who are also trying to understand something that may not be 25,000 light years away, but it is deep in the ground and we can also not see very much. And everything that we see is also distorted by what's between us and whatever we're trying to observe. So there's some really interesting similarities there maybe too.
Absolutely. And in fact, in the techniques that are much more modern in terms of what we do, which are called adaptive optics, so it's a hardware solution to correcting for the distorting effects of the Earth's atmosphere, these techniques are now being used in vision science. So people who want to study the retina, so imaging through the eyeball, which is a turbulent medium. It's also used in communication, so say through various say optical lines where you have distortion, or of course the military also cares about observing up and down. So there's I think in terms of the overall technique, there's a lot of interesting connections.
I was going to ask you about spin-off of this work into other areas. So you already answered that question. That's great. So let me go back to something I've been wanting to ask you. Your life in research has been one of discoveries and many things that were probably very surprising to you and hard to predict. But I'm going to ask you to predict out maybe 10, 15 years from now. So if we could teleport ourselves, into the future, and you look back, what do you hope to have found out then that you don't know at this moment yet? What would be the most exciting thing for you?
One of the things that we're after is going the next step with these orbits. So today, the initial work was all done on a pretty classical model of an orbit using Kepler's laws, or basically just Newton's version of physics. But over time, as well as with larger telescopes, one should be able to probe more fundamentally how gravity works. So Einstein's ideas about gravity. And the reason this is such an interesting question around a black hole is that that at some point Einstein's laws have to break down. Black holes are fundamentally represent our inability to make the laws of gravity work together with the laws of quantum mechanics. That's one of the reasons that black holes get so much attention. And these projects that on orbits allow you, with increased precision and increased patience, to look at some of these to make tests that haven't been possible before. And of course, the hope is that at one point you start to see the emergence of the deviation from Einstein's models so that you can start to get a handle on that more complete description of gravity. So that would be my hope for the next 10 years. We'll see what actually happens.
Well, that would be incredible. that is one of the reasons why I'm fascinated by black holes, because they're really, I would say, literally at the edge of science. There's so much we don't understand, so it's very exciting. And like I said, like you. I studied mathematics, but I never went into physics afterwards. I stayed with math. But let me take you back to your early days. I mean, you said that you started studying mathematics. I read in a little blog about your career that you had aspirations to be an astronaut and maybe even a ballerina before that. And we have many people listening to this talk, many girls particularly, who are thinking about what to study next. And so, tell us a little bit more about this way in which you developed those interests and decided to study math and then go to physics, and how that worked for you, and who supported you in this. Maybe with an eye on giving some advice to the young girls that are listening and thinking about their future careers in these fields.
Oh, thanks so much for that question. And I think it's so important to talk about these things, um, because it can look so pre-planned, and yet it's not. At least that's not my story. My story is not one of knowing precisely what I wanted to do from an early age. And I think that's why I often talk about where I can pinpoint the early interest, but also that simultaneously I wanted to be a ballet dancer. So it wasn't clear to me that I was going to go into astrophysics at all. Um, what I think what was apparent to me fairly early on is just a love of puzzles. I mean, I love jigsaw puzzles, crossword puzzles, Sudoku, whatever kind of, especially the logic puzzles. That emerged as something I enjoyed. And I think in terms of thinking about um, our paths, and our paths are never done. I mean, we're all evolving professionally and personally throughout our whole lives. So we're constantly asking ourselves, what is it that I enjoy doing, where is it that I want to go? So for me, understanding that I had a passion and an enjoyment, that I found numbers and logic a place of just pleasure. And that's how I think I identified my early interest in math. And then by the time I got to college, it was, it expanded. I mean, by taking classes, I think you try to figure out, well, what is this version of something you enjoy? Where's the place that really floats your boat, or that you have curiosity about. So for me, that was, I think, it's a slow evolution of just enjoying math and science, and trying to figure out what it is, and about math and science that I really did enjoy, and just to continue to try things that pushes your boundaries, in the sense that discovery, as a scientist, we think a lot about discovery in the boundaries of knowledge, but I think there's also the boundaries of your comfort. And so much of our growth as professional comes from pushing our personal boundaries. So one of the stories I like to share, and is that one of the things that when I went to graduate school that I had the biggest fear of was public speaking. So in fact, I went to Caltech in part because it was one of the graduate schools that didn't force me to do teaching, to do a teaching assistance. I mean, I really did not like public speaking. And my first year in graduate school, I had to give my first public talk. I think I shook from my head to my toes. And my PhD advisor said, you got to teach. Just, you got to get over this. And so I did teach, and I did discover through that I loved teaching. So I really went from actively avoiding this realm of teaching because it forced me to do something I was afraid of, to really understanding that I really enjoyed it. And I find it actually a really, I find doing research in the university setting just an amazing place to do research, because not only are we discovering new knowledge, but we're also helping new knowledge develop through teaching. And I think students always ask you, keep you on your toes. They're always asking you why. Well, actually, this is kind of, I really resonated with the previous speaker. Why is it that we're doing what we're doing? This is what students are really good at asking you, just in terms of just getting up to speed with what your group is doing. You're always being forced to answer that question, and I think that's a really good question to keep asking yourself. Why is it that we do it this way? Why is it that we're still pursuing these questions? What is it that would keep this research fresh? But apropos of the original question, you never know, and it's so important to both explore what you like to do, to keep exploring things that are new and you don't know that you might like. Because of course, how do you know what you'd like to do, and how do you know what you know until you've tried it? And then the third piece that I always like to think about in terms of professional development is how do we also give back? So there's sort of three parts of that, figuring out and articulating what today you enjoy, how to take new risks to further grow, and then how do you give back? And to constantly ask yourself that. I think today, there's sort of a overall rule of, every 5 years or so you should check in. And early in life, there are some really natural breakpoints, in the sense that there's high school, which is 4 years. So that transition to college forces you to think about those opportunities. And when we finish college, there's another break point where there's a reassessment point. But I think even as we continue to go through life, to continue to ask yourself that question of where, today, 5 years later, what is it that you still enjoy, and what is it that you could still learn? So that's
I
my
love,
that's my
I
two
love,
cents question.
yeah, I love your comments about the continuous learning. And also what I find very inspirational is your thought, your belief in, hey, if you're afraid of something, just jump in it and try it anyway, like with your communication. And just, I think you would enjoy hearing this. When I was talking to one of my colleagues in physics at Stanford University about this meeting with you today, she says, "Oh, I listened to her speak over 20 years ago, and I still remember she was such a great communicator." So you learned a lot from that early exploration. Hey, Andrea, it's been wonderful to talk to you. I think we could have continued this for a long period. I had a lot more questions to ask, but this was great. Thank you again for joining us. And have a wonderful rest of your Sunday. And I hope you can stay with us for a bit and enjoy some of the other talks that we have in the program. Thanks again.
Thanks so much, Marco. That was really a lot of fun.